this is the overview of electromagnetics. So basically, the electromagnetics is a mixture of classical physics and quantum physics, like classical physics and new physics. I'm not saying quantum physics, classical physics and new physics. So our classical physics, as a part of classical electromagnetics, is all based on the Maxwell's equations. So in our syllabus of net, JRF, GET and JEST, etc., uh, we have divided the electromagnetics in some parts. The first one is electrostatics, second one is magnetostatic, third one is electromagnetic waves, and the fourth one is geometric optics. So, in the last 5 lectures, we have discussed on this electrostatics. So, those lectures were all about electrostate, and now we are moving ahead. From this lecture, I'm going to start magnetostate. Magnetostatics, the second part of your electromagnetics, equally important to the electrostate. So this we are going to start today, and the third part is electromagnetic waves, in which we have to study the transmission line theory and Kirchhoff laws also. And these two are based on the circuit theory, and in this circuit theory, we will use some input from other disciplines too, like we will use some theorems from electronics too. Okay. And the last part is geometric optics, which is not in our syllabus. So we will not study about this part. Okay. This one we have done. This is what I'm going to start today, and this will be the next one. So this is some slides, previous slides will be the intro of the magnetostate. So please listen carefully. Most of the things you may know, you have studied in your previous classes too, but just listen carefully. There are some theories which we have to use while solving the questions. So magnetostatics is the branch of electromagnetics dealing with the effects of electric charges in steady motion. What do you understand by steady motion? Steady motion means the charge is not in any motion. It is in its steady state. It is stopped somewhere. It is not moving. Okay. So for the it is the branch when we are moving, we are dealing with steady motion, like steady current or direct current, DC. So we have talked about electrostatics. In electrostatics, there was a point charge. We were dealing with a point charge, and some electric waves were coming out from those charge, their charge, and some waves were going inside in that charge. And we were saying that those are electric field lines, and an electric field is generating around to the charge. That charge was constant at any point. But if we will talk about spin, if we will talk about rotation, if we will talk about vibration, and if we will talk about velocity of the charge, then we'll talk about magnetostate. The fundamental law of magnetostate is Ampere's law of force. We will study this law, and the Ampere's law of force is quite similar to the Coulomb's law, which we have studied. So in magnetostatics, the magnetic field is produced by steady current. The magnetostatic field does not allow for inductive coupling between circuits. If there are two circuits and we want to couple them by induction, then we can't do that in our magnetostatic branch. Second one is coupling between electric and magnetic field. That is not possible in magnetostates, but that is possible in electromagnetic theory using Maxwell's equations. So we will do later on. So we are starting with the Ampere's law of force. What is that law? So Ampere's law of force is law of action between current carrying circuits. Current carrying circuits. Any circuit which have some current, any circuit possessing some free charges which are flowing and producing current, then the law of action we can use is Ampere's law of force. Okay, so what Ampere's law tells us? Ampere's law gives the magnetic force between two current carrying circuits, or two current carrying wires, or two current carrying plates, or some similar things. Ampere's law of force involves complete circuit since current must flow in closed loops. There is a current in closed loop, so we can calculate that too from Ampere's law. So what Ampere's law is? If there are two parallel wires and they have some current I, like I am saying this wire having some current I1 and this is the another wire having some current I2, and those parallel wires carrying the current in the same direction, like if the direction of the current in this wire is like this one, and in this wire is also like this one, then they will always attract, the forces will between them will be attractive force. The second assumption is when two parallel wires having current in opposite directions, like the current is in it, for this one the current is inside, like the cross, when I will use the cross, that means inward direction, that means down to this page. Okay, and when I will use this dot, okay, then outward direction, that means up to this page. So this, for this the current is in inward direction, for this the current is in outward direction, so the direction of current is different in these two wires, and that's why the force between them will be opposite direction, or repelling, those wires will be repelling each other. Now if a short current carrying wire oriented perpendicular to a long current carrying wire. So this is a current carrying wire, current having current I1, and this is another current carrying wire having current I2. The wire is in this plane, and this wire is on this plane. Like these two are perpendicular to each other. Then what will happen? The force between them will be zero in this situation. Okay, so these small things you will have to remember, so that you can solve many questions from GAT paper and from BRC paper. These questions are mostly asked. So the experimental facts for Ampere's law of force are: the magnitude of force is inversely proportional to the distance squared, and the magnitude of force is proportional to the product of currents carried by the two wires. Okay, so when we are talking about the law, what we are doing, we are considering some direction so that we can establish or assume any force between them. So the direction of force established by the experimental facts can be mathematically represented by, like, if I have a force F12 having the direction A cap. Okay, so what is this A cap F12? This is unit vector in direction of force on I2 due to I1. F12 means the force is on I2 due to I1. It will always be equal to A2 cap. A2 cap is a vector direction of current I2 cross A1 cap cross A R12. So this A1 cap is vector direction of current I1, and this R12 is a vector direction of 2 from I1. When we are observing from I1 and we are at 2, then this R12 we will introduce. So this is the important equation. We'll use this equation in our magnetic moment and so, but we have to study it in our Ampere's law. So starting with this equation, this is the Ampere's law. We are moving ahead. So, what we want to find out, the force acting on a current element I2dL2. What is this I2dL2? That is current for some infinitesimal length dL2. Current I2 for some infinitesimal length dL2 by a current element I1 dL1 is given by. So the what will be that force? That force will be F12 equal to mu naught upon 4 pi I2 dL2 means A1 cross A2 cross A R12. We have used that equation which we have previously seen, and upon R12 square. Okay, so this is the original form of Ampere's law of force, but using some conditions, scientists have contracted this form, and the Ampere's law may also be written as, okay, this is for double integration if we are using two different currents, I1 and I2, and two different infinitesimal lengths dl1 and dl2, then we can write it as so. This is the with the analogy of Newton's third law, action reaction. We can see we have done the same what we have done in Coulomb's law. So in Ampere's law also, if we want to calculate the force on wire F wire 1 due to 2, like F21, that will be equal to opposite direction of the force on wire 2 due to 1. Okay, so this was this is the analogy of Newton's third law. This is also some important result. Yeah, so by introducing the magnetic flux density, we will reduce the Ampere's law. And how we will do that? Let's see. So first of all, we will study about magnetic flux density. We have studied about electric flux. So do you guys know what is the electric flux? Anyone can tell me? We have studied many times about electric flux, and you have calculated electric flux because you have done your assignments, no? So please tell me, what is electric flux? What is
And number
electric flux?
of electric field lines passing through an particular area.
Yes, okay. Anyone else? Okay, yeah, Aarti, you are right. So the electric flux was a number of electric field lines passing through some unit area or the some area we have specified. Here, magnetic flux have the same definition as electric flux was. The magnetic field lines passing with some infinitesimal area is your magnetic flux. So what will be the magnetic flux density? So Ampere's first law describes an action at a distance. Okay, action at a distance, which is analogous to Coulomb's law. What was Coulomb's law? In Coulomb's law, it was useful to introduce the concept of electric field to describe the interaction between charges. Now, in Ampere's law, we can define an appropriate field that may be regarded as the means by which current exert force on each other. Electric field was force between two charges. Ampere's law is about force between two currents. Okay, this is the major difference, and this difference will be useful while we will solve the question. So, the what will be the magnetic flux density? We have seen this formula now. F12 is equal to integral C2 I2 dl2. What is this C2 and C1? C2 is closed loop for the second current carrying conductor, and C1 is the closed loop for the first current carrying conductor. So F12 is equal to integral C2 I2 dl2 cross mu naught over 4 pi integral I1 dl1 cross A R12 over R12 square. So this I2 dl2 is same, and all this stuff I am writing as B12. B12. This B12 is your magnetic field. We will define it in Biot-Savart Law 2. This B12 is equal to this one. How we are getting this? This is your Biot-Savart Law. We will study soon. So if we can write it as integral C2 I2 dl2 cross B12, then this B12 is this one, and this B12 is your magnetic flux density at the location of dl2 due to current I1 in loop C1. And this result is coming from your Biot-Savart law. We'll see how it is coming. Now, can we derive that? Yes, we are trying to. Suppose that an infinitesimal current element ideal is immersed in a region of magnetic flux density B. The current element experiences a force dF by dF equals to, what is dF? We have studied dF was equal to ideal cross B. This was the equation we were getting. So dF equals to ideal cross B we can write, and hence what will be F? Just what we will do, we will integrate. So F will be equal to I integral dl cross B. Okay. So this was the force due to magnetic flux density B, total force exerted on a circuit C, having current I, having a closed loop or an open loop like a circuit. Okay. So do you guys know that a circuit is always a closed loop? That is why if the circuit is opened, then there is no current in that circuit. So obviously, so circuit is always a closed loop. Okay, moving ahead, let us introduce Lorentz force. You have studied many times about Lorentz force. At least you have heard the name Lorentz force from somewhere. So what is that? If a point charge is moving in a region where both electric and magnetic fields exist, then it experiences a total force given by F equals to Fe plus Fm. Fe means electric force, and there is a plus sign here, and plus Fm. Fm is force, magnetic force. So Fe, we have studied in our electrostate that the electric force was QE, Q into E, charge into electric field. So what is your Fm? Here is also a plus sign. So Fm is Q into V cross B, magnetic flux density cross the velocity of that charge. The charge is Q. So the Lorentz force is basically the combination of electric force and magnetic force. The electric force we can write as QE, the magnetic force we can write as QV cross B, and thus we are getting the Lorentz force F equals to QE plus V cross B. Yeah. Okay, so let's come to the important topic, that is Biot-Savart law. So guys, the Ampere's law and the Biot-Savart law both are coming in your exams. Alternatively, the questions are coming like sometime the Ampere's law application is coming, sometime the Biot-Savart's law application is coming. So please do this stuff quite good understanding so that you can solve the questions. The questions from magnetostates are quite easy. You will find the questions of magnetostate relatively easy to electrostate, and all those questions will be on your basic knowledge, based on the basic knowledge. So magnetostate is a scoring branch, so study it and do some hard work with this magnetostate so that you can get the title next year. Okay, so the Biot-Savart law gives us the magnetic field arising at a specific point P from a given current distribution. It is basically a fundamental law of magnetostate. So what is that Biot-Savart law? I have told you that we will use this equation again in our Biot-Savart law. So this was the equation, dB equals to mu naught over 4 pi I dl cross R over R2. R is the conventional direction, and this R square, this R over R vector will be the conventional direction, and R square will be the distance between the point at the wire. So yeah, this is the diagrammatic representation. So this is a point P situated at some distance capital R from one point of a wire and at some distance small r at another point from a wire. This is the wire. Okay, it have some current. It is a current carrying wire, so it have some current in this direction. The arrow is representing the direction of current. If we are taking any infinitesimal length of this wire, like I am not talking about the whole length, I will cut the wire into pieces and I will select one piece, and that one piece having the distance dl, this piece, this distance, this is your dl. Okay, if this is your dl, then the magnetic field due to this wire on this point will be what? The magnetic field will be this one. We are equal to integral mu naught over 4 pi I dl cross r over q. Okay. So you have studied about Ampere's law, you have studied about Biot-Savart's law. So now we'll study about the types of current distributions. Um, this is also quite similar to the type of electric current distributions we have studied now. There were some surface charge, there were some charge densities in electrostate. Three types of charge densities were there. Do you remember? Anyone can tell me? In electrostate we have studied about different types of charge densities for different surfaces. So what were those?
Ma'am, line charge density, surface charge density, and volume charge density.
Yes, good. These three were line charge density, surface charge density, and volume charge density. Here, again in magnetostate, we can introduce three types of current distributions. Those are quite similar to that electrostatic charge densities. The first one is line current density, occurs for infinitesimal thin filamentary bodies like wires. Okay, line charge density है तो wires के लिए ही होगी. So the first one is line charge density, second one is line current density, second one is surface current density. Surface current density means current per unit width that occurs when body is perfectly conducting. And the third one is volume current density, that means current per unit cross sectional area. Most generally we will use this one, volume current density. Okay, because we will be talking about some unit cross sectional area in most of our questions, and that is why we have to use this volume current density. Okay, so moving ahead, for a surface distribution of current, the Biot-Savart law becomes this one. If we are talking about any surface, then we will be introducing the surface current density, and this is the notation of surface current density, Js. Okay, if anywhere you see the name surface current density, then you will use the notation Js, and this ds is for your unit surface element. And I have told you that mostly this equation will be followed for conductors. Next, for a volume distribution of current, the Biot-Savart law becomes this one. This is J R dash, which is volume current density, the notation for volume current density. Somewhere we can write it as JV R dash. V is in this suffix, and this dV dash is that infinitesimal volume element. Mostly we will use this formula. So this formula is important. You guys can remember this formula. Okay. So somewhere, sometimes in exam and sometimes in your interview, the question is asked, can you write Ampere's law in integral form? We have already written Gauss law in differential form and in integral form too in electrostate. So this Ampere circuital law can also be written in integral form. So the integral form is the constant function of current distribution. the circulation is computed. So the formula to remember is in close integral B dot dl equal to mu naught I enclosed. This is ENCL. I ENCL. What does this means? I enclosed means the current in any closed circuit or in any closed loop. This is your I enclosed. Okay. So the Ampere circuital law in its integral form is this one. This is your integral form. You have seen this equation in your 12th standard too. Okay. So the Ampere circuital law we have written in integral form. If we can introduce different current densities like surface charge densities or volume charge densities, then how can we write this law? So the volume charge densities in the current in volume charge densities I enclosed equals to is taken to be in direction defined by right hand rule applied to dl. Right hand rule, you know, or we can also discuss on it. So this I enclosed for surface charge density, if we will apply to the Ampere's law, then what will be the form? So the form will be uh, so C B dot dl equal to mu naught. Okay, this is your mu, or here was I na, so I can write it as S J ds. Okay, so in surface charge density format we can write this equation as this one. Okay, so Ampere's law and Gauss law, is there any similarity? Just as Gauss law follows from Coulomb's law, so Ampere's circuital law follows from Ampere's force law, obviously. Just as Gauss law can be used to derive the electrostatic field from symmetric charge distribution, Ampere's law can be used to derive the magnetostatic field from symmetric current distribution. These two are the major differences. So, okay, moving ahead, we'll now study the applications of Ampere's law, important topic, and I'll not tell you in vast, just briefly we'll see some applications. So, Ampere's law in integral form is an integral equation for unknown magnetic flux. Like if we don't know the magnetic flux B, na, so if we don't know the magnetic flux or magnetic field B, then we can calculate using this circuital law. If current is given, then we can find out B. If B is given, then we can find out the current and so on. So, how to calculate the magnetic flux density of an infinite line current using Ampere's law. This is your first application. What is that application? The application is saying you can use Ampere's law to calculate the value of B, magnetic flux density, for an infinite line carrying some current I. Okay, for an infinite long wire, we can say, and having some line current I. So consider an infinite line current along Z axis carrying current in positive Z direction. It is this. The current is in positive Z direction. So, symmetrically, we will assume some things. First one is assume from symmetry and the right hand rule from the the form of the field. Okay, so these assumption and this example I have taken from your book Griffiths, the introduction of electrodynamics. So you can see this example from there also. Just one, assume from symmetry and the right hand rule, the form of field will be B equals to, okay. So what is this A phi? You have studied, you know that if you are working with line charge or line current, then the symmetry for that line is cylindrical. You have studied that for line, the symmetry is cylindrical. In Gauss law, I have told you various types of symmetry and how to make those. So if the symmetry is cylindrical, then we can use the cylindrical coordinates too. So in cylindrical coordinates, three notations we use: rho, phi, and z. Okay, you know this thing. So the phi is for the angle, and that rho is for the distance. So using the cylindrical coordinates, we can write it as this one. And second one is we have to construct a family of Amperian paths. So we will put a boundary. The rho is greater than equal to 0 and less than equal to infinite, where for this symmetry, the rho is the radius of that conventional circles, or those conventional circles of that cylinder. And the third step we will do, evaluate the total current passing through the surface bounded by the Amperian path. Like this was your wire, line wire, and the conventional symmetry we are making, a cylinder we are making as a conventional symmetry, and we have to find out the total current. This is the current carrying wire now, so the wire has the current I, and this symmetry, this is the conventional or imaginary symmetry. This symmetry is called Amperian path. This one, Amperian path. Okay, there was some Gauss law in electrostate. Here is Amperian path. For this Amperian path, the total current will be equal to this current, this I, the value of I, the value of the current in that wire. So I enclosed will be equal to integral J dot ds. So this is our Amperian path, and the things I have explained is in this diagram. Okay, so we have calculated the value of I enclosed. Now, for each Amperian path, evaluate the integral. We can integrate B dot dl as B dot L. dl is the small fraction of length. So if we want to integrate small fraction, integrate means addition. The another meaning of integration in mathematics is to add them. So if we add those small fractions, then we can get the whole line. So BL, the L is the length of Amperian path and B is the magnitude of Amperian path. So the value of B I will put here and the value of this length L. So the symmetry is circle. You can see this is a circle. Okay, this is a circle. So for a circle, the length is the circumference of that circle, that is 2 pi r, and I can write it as close integral B dot dl equals to B rho 2 pi rho, because rho is the radius we are assuming. Okay, and at last we can solve. B equals to mu naught I enclosed, and just put those answers, and I am getting B equals to A5 mu naught I over 2 pi rho. You can also calculate this. So that was one equation. Now applying Stokes theorem to Ampere's law. You have studied Stokes theorem and Gauss theorem in electrostate. We can use that theorem in magnetostatics also. What was that theorem? That theorem was the line integral of any vector quantity can be changed into the surface integral of the curl of that vector quantity. Okay, so integral of C B dot dl will be equal to integral of F, integral of S del cross B dot ds. So this B dot dl was equal to mu naught I enclosed, and I enclosed was equal to integral J dot ds. So just compare these two terms, this one and this one. So while we are comparing these two terms, this ds is similar. Okay, the integral is similar. Okay, so what we are getting? We are getting del cross B equals to mu naught J. This is the differential form of your Ampere's law. So what we have studied? We have studied the Ampere's law, the Ampere's circuital law, the integral form of Ampere's law, the differential form of Ampere's law, and one application of Ampere's law. So that was the differential form of Ampere's law. Okay. So, making some fundamental postulate, the differential form is making fundamental postulates of magnetostate, which are Ampere's law, and differential form is this: no isolated, if there is no isolated magnetic charge, that means no current density, that means J is zero. If J is zero, then del cross B is also zero and del dot B is also zero. If del dot B is also zero, then B is solenoidal. Okay, so if in your exam question is coming that the four values of B is given and you have to calculate which one is solenoidal quantity, so you can just do the derivative of that magnetic field quantity and put it equal to zero. If it is coming zero, then it is solenoidal. And okay, what is vector magnetic potential? The new term, magnetic potential. And let me tell you, the term magnetic potential is not as similar as electric potential. There was electric potential means was the unit in volts, but the magnetic potential is quite different. So vector identity, the divergence of curl of any vector field is identically zero. Divergence of curl of any vector is zero. If the divergence of a vector field is identically zero, then that vector field can be written as curl of some vector potential field. If divergence of any quantity is zero, then that quantity can be written as the curl of any other quantity. So we can see this. This is the corollary. So from here, we are getting magnetic vector potential or vector magnetic potential. Since the magnetic flux density is solenoidal, like if del dot B equals to 0, then we can say that a magnetic flux density is solenoidal. So if del dot B equals to 0, then B can be written as B equals to del cross A. So this A is your magnetic vector potential, a new quantity. Magnetic vector potential, this is also a vector quantity. Okay, so if you have given this A and you have to find out this B, then you can find out easily. If this A is in any coordinate, like you have given Cartesian coordinate, then this delta you will use in Cartesian coordinate. If this A is in spherical coordinate, then this delta you will use in spherical coordinate, and so on. Okay, so yeah, this was the general form of Biot-Savart law, and in this general form, this R over R cube, the value of this R over R cube is quite similar to del dot 1 upon R. This is the inequality of mathematical. You have studied already. So okay. So you can write instead of R over R cube like del dot 1 upon R, and del dot 1 upon R is here, JR dash is here, so you are getting del cross JR dash over R. What is this? Next, we have put instead of R over R cube, del 1 over R, and the term we are getting is this. Hence, we have BR equals to del cross mu naught over 4 pi integral JR dash over R dV. Okay. So this is the same. Okay. Next topic is our magnetic dipole. Yeah, the magnetic dipole is quite similar to the term electric dipole. So if anyone can tell me what was electric dipole, come on, please answer. What is the electric dipole? What is the electric dipole? And what is the mathematical formula of electric dipole? You don't know. Okay, पढ़ लेना. जब पढ़ो समझ में आ जाए तो बता देना, ना आए तो भी बता देना। चलो मैग्नेटिक डायपोल देखते हैं। सो अ मैग्नेटिक डायपोल comprises a small current carrying loop. So the magnetic dipole is quite similar to the electric dipole. The electric dipole was the system of two charges having some small distance between them, and we were considering those two charges as a system and treating them as one charge, as one dipole. But the magnetic dipole is the combination of small current carrying loop. We will not talk here about any charge. We will talk here about some current. Okay, so as the electric dipole was a charge monopole, the magnetic dipole is the simplest source of magnetostatic field. Okay, and there is no magnetic monopole. There is always a dipole. Okay, so how we can represent that, and the magnetic dipole is analogous to electric dipole. I told you, just as the electric dipole is useful in helping us to understand the behavior of dielectric materials, obviously, so the magnetic dipole is useful in helping us to understand the behavior of magnetic materials. Okay, if you want to study the magnetic materials, then we have to study the magnetic dipole. Yeah, so consider a small circular loop of radius b. Look at this loop. It has some radius b carrying a steady current I. Let's suppose the current is in this direction. Assume that the wire radius has a negligible cross section. This radius has a negligible cross section. So the electric dipole was this type, equals to kp over r cube. This is in spherical polar coordinates. So P equals to electric dipole moment, that was equal to Q dot T. So the magnetic dipole moment will be M equals to AZ is the conventional direction, I pi B square, or we can say I dot area. And the area for a circle is pi r square, and we were considering B as the radius of that loop. So pi b square will be the area. So M equals to I pi b square. Basically, the magnetic dipole moment, the formula of magnetic dipole moment, M is equals to I dot A. A is area, I is current. Okay, so we can write the vector magnetic potential in terms of magnetic dipole moment. Like if we have vector magnetic potential A equals to mu naught m psi theta or 4 pi r square, I can write it as mu naught m cross ar or 4 pi square. Then we can write the field in terms of magnetic dipole moment as B equals to from where it is coming. It is coming from del cross A, and I am write it as this one. This is some mathematical. If the B field means the magnetic field is solenoidal, then we are getting del dot B equals to 0. So physically this means that magnetic charges do not exist. A magnetic charge can be viewed as an isolated magnetic pole. So if there is no magnetic charge, there is no magnetic monopole. So there is always a magnetic dipole. No matter how small the magnetic is divided, it always has a north pole and south pole. If this is a magnet, let's suppose, and I am cutting this magnet like this one. This one I have cut into two pieces. Those two pieces separately will be two different magnets. They will themselves induce another pole, north pole and south pole, and hence it is proved that there is no monopole exist in magnetic field. Yeah, always there is a dipole. It is dipole. Dipole means two poles, na? There are two poles, so it is dipole. It is also a dipole. Okay, there are always two poles. Okay, what is magnetic flux? Obviously, you know now the magnetic flux goes crossing an open surface as is given by their electric flux was phi. Here, magnetic flux is psi. Psi equals to integral V dot ds. This psi is in the unit of Weber. WB means Weber. and this B is in the units of Weber per meter square. Okay. So the net magnetic flux leaving any closed surface area is zero. Like if del dot B is equals to zero, then from Gauss differential theorem del dot B, if I'm doing some volume integral, it will also be zero. So the differential form of Gauss is saying that B dot ds will be equal to zero. That means for a closed loop, the magnetic flux density, there's no magnetic flux density, there will be no magnetic flux density for a closed loop, as closed integral B dot ds is zero. And this is the relation between magnetic flux and vector magnetic potential. Just to put del cross A instead of this B, del cross A dot ds, and just convert from Stokes-Cowl theorem, you can get this one. So the psi means magnetic flux is also equal to integral C A dot dl. Okay. So uh, yeah. So this was from theory portion. Now we will do some questions, and they are gonna be interesting. The question one is the magnetic field corresponding to the vector potential, and the vector potential is given A equals to 1 by 2 F cross R plus 10 by R cube R vector, where F vector is a constant vector is. We have to find out magnetic field. That means we have to find out the value of B, and A is given. So you know the formula. B equals to del cross A. But this A is in its vector form, and it is the combination of two vectors F and R. So just this is A, just do the stuff. B equals to del cross A, you know. So del cross, and A means this whole, this value, put this, and separate, use the cross. Like if F cross R, I am applying del cross curl over this F cross R, then this will be one vector, second vector, third vector. So you know the recipe in mathematical, if you have studied. It is R dot del dot F minus R divergence of F. So, okay, so this one. You can use this one and get the answer. Again, R dot del means this one. R dot del dot F, this one. Divergence F is 0. F dot del means F dot the value of del, and dot R, then this one. So you are getting divergence of R equals to 3. One by one, put all these values, and at last you will get the answer X. Please do this question on your notebook, and okay, please practice as more as possible of these questions based on the formula B equals to del cross A. The A can be any form. Okay, so this question was from NET June 2012. Next question is from NET June 2012 again. The magnetic field at a distance r from long straight wire carrying a steady current I is. So we have to use the Ampere circuital law. What we have given? We have given there is a long straight wire, and at some distance r, okay, there is a point. On this point, we have to calculate the magnetic field for this current carrying wire. Okay. So we will use the Ampere circuital law, which is B dot dl equals to mu naught I. This, okay, from a long straight wire carrying a steady current. Okay. So B dot, why 2 pi r? You know this thing, because the wire is having the line current density. That is why the conventional Amperian loop will be the cylinder, and for this cylinder we will talk about some discs, those small discs. For one disc we will talk about the circumference, and the circumference having radius r will be 2 pi r. So the length will be 2 pi r, obviously. So B dot 2 pi r equals to mu naught I, and B equals to mu naught I over r. So the proportionality is asked now. So the right answer will be option number D, I upon r. This was an easy question. Next question is the vector potential. Okay, again the same question. A is given and you have to calculate magnetic field. That means B. So the vector potential due to magnetic moment M at a point R is given by A. If M is directed along positive Z axis, the X component of magnetic field at point R is, you know the recipe, what you have to do, B equals to del cross A. So just one by one, you have to apply this curl on different terms. You have applied U dot A, you have applied on A cross B. You are getting these types of result. You have applied this curl on 1 over R cube M cross R. Then you are getting this one del cross M cross R. Then you are getting this term and so at last you will get you have to mix all those results and at last you will get this whole stuff. Now the question is saying we have to calculate the x component of magnetic field. So the x component means the term having I cap. So this is your I cap. So x and z you will involve in this 3m over r5 and the rest is of no use for this question. So this is the answer. So the correct answer for this question is C. Okay, next question. Consider an infinite conducting sheet and what is this? Infinite sheet in xy plane with the time dependent current density. Okay, KTI, where K is a constant, the vector potential at XYZ is given by. Okay, we have given this vector potential again. You have to calculate the magnetic field. Now you know the recipe. What you will do? You will do B equals to del cross A. Just do that and calculate. So it is quite easy. This question was from December 2012. Okay, the next question is if A equals to yzik plus zxzgk plus xykk and C is circle of unit radius in plane defined by z equals to 1 with the center on z axis, then the value of integral close integral C A dot dl is, and there are four options. So you have to calculate this value. This is the term of from Ampere Circuital law we have studied. You have given A. So what you will do, what you think you can do, you have to find out the value of A dot dl, and you know that A dot dl equals to uh, uh, this A dot dl equals to mu naught I. So first you can find out the current, or if you can find out from somewhere the magnetic field, then you can also do this. So this A is given, so you can easily do this curl of A. This curl of A is coming 0. You can see A is 0. A is conservative vector field and its line integral around a closed loop will also be 0. So there is a trick for this question. What is that trick? That trick is if del cross A equals to 0, if del cross A is equal to 0, then integral A dot dl will also be equal to 0. Just remember this thing. If you know this one, you can calculate this one. If you know this one, you can calculate this one. Okay. So the option number 4 will be right for this question. This was from NET June 2014 and there were many questions I have not included because all those questions were quite similar. You can solve them and tell me whether you are able or not. Any query you can ask. No query?
Ma'am,
Yes.
in one of the question that a straight wire
Hmm.
conducting has a current, so magnetic field is cylindrical. We can assume.
We can
So
assume no magnetic field is cylindrical. We have not to assume. We will assume the empirical loop or the conventional symmetry as cylinder.
okay. So
We
ma'am,
will not assume magnetic field. Hmm. Yes, tell me your question.
If problem is that current is conducting current wire is also
Uh,
in a loop. So what is magnetic field? What about magnetic field?
Current conducting wire is also in a loop, means there
Yes.
is a loop already there, and you are putting some current conducting wire inside that loop. Yes, you are saying
No,
that.
no, ma'am.
So,
Here, wire is straight, okay?
okay,
But
wire is straight.
what if wire is not straight line, not straight? It
Okay.
is
If the wire
in a
is
loop.
circular or in any symmetry.
Yes, yes, like
Yes,
solenoid or something.
yes. You will get the answer in my next lecture, because in the next lecture we will talk about the applications of Biot-Savart law, and in that part we will use those circular, spherical shell symmetries. All those questions we will do. Don't worry.
Okay.
Yeah. Anyone else? Yeah. If no queries, I am